So good evening. So we are discussing Young's modulus. So yesterday we discussed some of the top points related to Young's modulus. Almost these are all the points we discussed regarding Young's modulus. Right, we will recall the formula y is equal to FL by A into E. So this is the expression for Young's modulus. So Young's modulus value does not depend on dimensions of the material, it depends on nature of the material. And Young's modulus value is infinity for rigid body because elongation in the case of rigid body will be equal to 0. Okay. Young's modulus is more, means which is more elastic material. Right. So in addition to that, we can take elongation is equal to FL by A into Y. So in the case of stretching and all, we discussed formula which is changes with respect to different materials or change in dimensions of the material, how elongation produced in different materials by stretching a wire. So in the case of stretching a wire, volume will remains constant. That we already discussed those cases. Now, if Young's modulus is numerically equal to stress. Young's modulus is numerically equal to stress. Then we know y is equal to stress by strain. Now from this we can write strain is equal to stress by y. Now what they are saying, Young's modulus is numerically equal to stress. So stress and Young's modulus both are same, which means that implies strain is equal to 1. So what is meant by strain? Elongation by original length is nothing but strain. E by L is equal to 1. So E is equal to L. Which means elongation produced in the wire is equal to original length of the wire. What it means, for example, we have taken a wire, so which is of length L. So now we are applying stress on this body, which is equal to Young's modulus. Now we are applying stress on your body, which is equal to Young's modulus. Now the elongation produced in the wire will becomes length of the wire. So this is what we call as elongation, which is equal to original length of the wire. That means, so what happened to the length of the wire becomes 2L. That means final length of the wire became double. So theoretically they asked the question, what happened when Young's modulus is numerically equal to strain? So what is the point we need to take it as? Final length. That means Young's modulus is numerically equal to stress. Final length is equal to double of its initial length. And elongation produced in the wire is equal to original length. That means elongation is equal to 100%. Elongation is equal to 100%. So these are the key points you need to get from this. Y is equal to stress. Okay. Final length is equal to double of its initial length, or elongation is equal to original length, or elongation is 100%. Young's modulus is equal to stress applied. Then these are the points we need to. Next point. If L1 and L2 are lengths of the wire, when tensions T1 and T2 are applied. L1 and L2 are lengths of the wire, when tensions T1 and T2 are applied. Then the natural length of the wire is natural length of the wire. So based on this point, they asked directly formula they asked in previous NEET examination. So L1 and L2 are lengths of the wire when tensions T1 and T2 are applied. The natural length of the wire is. What it means, for example, so initially you have taken a wire. So this is of length L. This is of length L. When T1 tension is applied, for example, this is mass M1, tension is T1. So when T1 tension is applied, tension is nothing but here weight of the body. There is M1G. So the wire is looking. So here length of the wire is L1. Whereas when T2 tension is applied, this is M2. So in this there will be T2 tension. The length is L2. Now this is original length. So when T1 tension is applied and T2 tension is applied, the length of the wires L1 and L2. Then what is the original length L of this wire? Now because of this tension T1, there is elongation E produced in this one. This we can write as E1. So because of tension T2, elongation produced in this is E2. Now this elongation is direct proportional to tension applied. So now we can take elongation is proportional to tension applied. So what is elongation? Final length minus initial length. So here what is final length is L1 is the length when T1 tension is applied. So original length is L. Elongation is final length minus initial length. That means L1 minus L is proportional to T1. That is equation number 1. In the same way, so here elongation, what is elongation here? Final length is L2, initial length is L. So L2 minus L is proportional to T2. And T2 tension is applied. So because elongation is proportional to tension applied. Now we can take some proportional constant by taking ratio, they will get cancelled. That means 2 by 1 or 1 by 2 whatever it is. So 2 by 1 will becomes L2 minus L by L1 minus L is equal to T2 by T1. That implies T1 L2 minus T1L is equal to T2 L1 minus T2L. Now that implies T2 we can bring this side. T1 L2 minus T2 L1 is equal to, this we need to bring this side, T1 L minus T2 L. Now here this implies T1 L2 minus T2 L1 by L is common, So T1 minus T2 is equal to L. So this is the expression for natural length of the wire. So when what they given, L1 and L2 are lengths of the wires and T1, T2 tensions are applied. Then what is the original length of the wire? So here the point what we need to consider is elongation is direct proportional to tension applied. So from this, in this first case, elongation is final length is L1, initial length is L. L1 minus L2 is equal to elongation is proportional to tension is T1. L2 minus L is proportional to T2. By taking this, we can get T1 L2, T1 L2 minus T2 L1 by T1 minus T2, which is equal to original length of the wire. So what is T1? T1 is nothing but M1 into G. What is T2? Is M2 into G. Now in the place of T1 and T2, they may ask, they may give the values of masses also, because this is M1G minus M2G by M1G minus M2G. So M1 L2 minus M2 L1 by M1 minus M2. So in terms of masses also they may ask the question. Okay. So in terms of masses they given in JEE mains examination. In terms of this direct formula they asked in previous NEET examination. So make a note of this. Next. Effective Young's modulus of effective Young's modulus of wires. First one, series arrangement of wires. You see here, this is a rigid support. This is of wire of length L1, Young's modulus Y1, Young's modulus Y1, and another wire of length L2, Y2. So here area of cross section is A. This is also area of cross section A. So in this case, we can take area of cross section is remains the same. So in series arrangement of wires, area of cross section remains same. Now because of this is Y1 and this is Y2, so Young's modulus is different, which means these are made up of different materials. So different materials, they have different Young's modulus and they will elongate differently. So this elongation produced in Y1 is E1. So Y2 we can get as E2. That means elongation is different. Elongation is different. So Young's modulus automatically different because these two are made up of different materials. So steel, copper, so iron, steel, or copper, iron, like that we can take any two different types of material because Young's modulus is depends on nature of the material. So as we know, what is the different parameter? From that different parameter, we are going to find the effective value. That is the key point we need to understand from the combination. So combination of resistors, in 7th standard you may study about combination of resistors. combination of capacitors, combination of inductors, combination of wires, whatever may be, the parameter which is different that we need to take from the different parameter we are going to find the effective value. Now, elongation is different because these two are made up of different materials. Now, so total elongation produced E is equal to E1 plus E2. E1 plus E2. So this is equation number 1. We know elongation E is equal to FL by A into Y. FL by A into Y. So what is F? What is F? So what is the force we are applying on both the wires will be same. That means we are attaching some weight here. This is nothing but weight acting on the combination of the wires. This force will be remains same. Now in the case of E, we can substitute F, the same force we are applying. Length is different, then we need to take L effective. So which is different parameter, further parameter we need to take effective value by area of cross section will be same, remains the same, area of cross section remains same, and Y is also effective because the X modulus, that is what we are going to find, which is equal to what is E1? E1 related to first wire, that means F L1 by A into Y1 plus F L2 by A into Y2. That means F by A will cancel, and we can get L effective, we can write as L1 plus L2 plus so on plus Ln in general term by Y effective is equal to, as this is series, we may represent the effective will be equal with the Y suffix X, X modulus in series combination of wires, which is equal to L1 by Y1 plus L2 by Y2 plus so on plus Ln by Yn. So this is a general expression in the case of number of wires. Okay. So here the point is elongation is different. Elongation is different. So from the different elongation expression, we are finding E is equal to E1 plus E2. So from this, from the basic expression of elongation, we are writing this. So which is different, further we need to write effective, and remaining we need to take as same. Okay. So L effect by A into Y effective, we can write like this. Right. If L1 is equal to L2 is equal to L, L1 is equal to L2 is equal to L. That means equal length of the wire. So length of the two wires will be equal. That is the case. General equation we have written. Now we are taking equal length of the wires. Now what done? L1 plus L2. Two wires taken, two wires means L plus L. L plus L, that is 2L by Ys is equal to L1 is L by Y1 plus L2 is also L by Y2. Therefore Ys is equal to 2Y1 Y2 by Y1 plus Y2. This is effective X modulus in series combination of the wires. So this is general formula. Otherwise, in the case of average speed, you have calculated N by V average is equal to 1 by V1 plus 1 by V2 plus 1 by V3 so on 1 by Vn. So like that, similar formula you will get in the case of average speed. So in capacity we need to identify this formula. So the point what we need to consider here is elongation is different. So from that elongation different point we have calculated all these expressions. So in series combination, effective X modulus is equal to 2Y1 Y2 by Y1 plus Y2 when two different wires of equal length are connected in series. Right. Next, second one. Parallel arrangement of wires. Parallel arrangement of wires. Now you can take a rigid support. So this is of wire. Of length L, X modulus Y1, area of cross section A1, area of cross section A1, and another wire also having same length but area of cross section is different, Young's modulus will be different. These are made up of different materials. Now with this combination we are attached one weight. So weight is equal to Young's. Weight is equal to, now here see, this is L, length of the wire, this is length of the wire. So length of the wire will be remains the same. Area of cross section will be different. Now whatever may be the stress which is applying on these two wires combinedly oppose that weight. That means which is balancing that stress what we apply. That means these two wires combinedly balances that weight what is hanging from this ends of the wires. That means stress is shared between the two values. That means elongation is same. Elongation is same since stress is shared between two wires. So what is the stress? Force by area. So we can take force what we are applying on that will be summation of the two forces. F is equal to F1 plus F2. As we know, that is equation number 1. As we know, elongation is equal to Fl by A into Y. From this we can write F is equal to A Y E by L. A Y E by L. Now in this expression we can write in the place of F, A, first we will write what is this? A F2 because A is different, Y F2 because Y is also different, elongation is the same, by length of the Y is also same. Elongation of Y is also same, length of the Y is also same, both are length are same. Now F1 means A1 Y1 E by L plus A2 Y2 E by L. So E by L, E by L, E by L. So E by L common and get it cancelled on both sides. Now this is equal. What is A effective? That means Y effective into A1 plus A2 plus so on plus AN is equal to A1 Y1 plus A2 Y2. Therefore, Y effective is nothing but YP is equal to plus so on plus AN YN. So now we can write as A1 Y1 plus A1 Y1 plus A2 Y2 plus so on plus AN YN by A1 plus A2 plus so on plus AN. So this is general expression for Young's modulus of parallel combination of the wires. Now, if area of cross section A1 is equal to AB is equal to A, then YB is equal to this is A, this is A, this is A, this is A plus A to A. That means A get cancelled. Then Y1 plus Y2 by 2. In the case of two wires, we can take so this is expression for effective Young's modulus in parallel combination of the wires or parallel arrangement of the wires. Okay, you see here, length is the same, area of cross section is different, elongation is the same. That means to become this weight will be remains the same, like remains horizontal, elongation should be same. Otherwise, if it is less elastic, means it will elongate more. So because of that, the end of the rod will come down. So that will not happen. So in general, this rod or this weight, what is hanging from these two bodies, will be remains in horizontal. So if that is the case, then elongation will remains same. So to become this elongation remains the same, the stress what we are applying in the form of this weight will be shared between these two. That means they will share among them to hold. That means both of them will try to hold that weight what is hanging from its ends of the wire. So that the reason stress is remains the same. That means stress is shared between the wires. Then we can take F is equal to F1 plus F2. So from the general expression, basic expression of Young's modulus, we can take elongation expression like this. From that we can calculate force. So from this force, which is different, that we can take effective value and we can calculate it Young's modulus like this. This is the general formula. So in the case of two wires having equal area of cross section, then YB is equal to Y1 plus Y2 by 2. Okay. So these are the points related to the concept of Young's modulus. So based on this, we need to practice some numericals. Okay, so once recall the main formula related to Young's modulus. Breaking stress and all we completed yesterday. Young's modulus. So this is Young's modulus. Longitudinal stress by longitudinal strain. F by A by delta L by L. So delta L we can also represent the elongation. So area of cross section we can represent with by R square when it is circular area of cross section. Okay. Right. So based on the L by R square we can find Young's modulus. So based on the Young's modulus we can say whether the material is elastic or more elastic. So comparatively for different materials elastic nature we can understand with the help of the value of Young's modulus. Okay. Right. Now Young's modulus is not defined only for solids. It does not define for liquids and gases because it is having only elongation of the wire will be possible only in solids. So Young's modulus value depends only on nature of the material but independent of dimensions of the material. Okay, so that is the reason we have taken different dimensions of same material. Young's modulus will remains same. And for rigid body, the separation between the two molecules will be remains the same. There is no elongation produced in the wire. So because of the reason, y is equal to infinity for a rigid body. Okay. So from this, as Young's modulus is not changing, so there will be different elongation of the wires based on that nature of the material. So now we are going to discuss about with respect to elongation, how elongation changes in the case of different materials. Okay. So now in the place of area of cross section we can take, if it is circular area of cross section we can take, in general wire is in the form of cylinder having circular area of cross section. That means C is proportional to L by R square. So by using this L by R square ratio, they will give different wires of different length and breadth. From them we need to identify which one having higher X modulus or lower X modulus. Okay. Or elongation, in which wire elongation is more. So elongation is more means X modulus is less. That means that is less elastic. So in the case of stretching of a wire, volume will remains constant. So volume is nothing but area of cross section into length of the wire. Area is equal to constant. Area of cross section increases means length will decreases. Length increases means area of cross section will decreases. So based on that, so elongation expression we are expressed in terms of volume. Now Fl square by V, as in the case of stretching, volume will remains constant. Then for the same material, elongation is proportional to L square. Then we can write E1 by E2 is equal to L1 by L2 whole square. In the same way, multiplying with the area of cross section, then we can get E is proportional to 1 by R to the power of 4. And in the case of volume will be remains constant, we can take Young's modulus is numerically equal to such these things we discussed today. Okay, and series and parallel combination of the wires and their effective Young's modulus. Okay. So these are the points we need to recall from the concept of Young's modulus. And there is another concept that also we will complete. Then we can go for solving of numericals. That is thermal stress. Thermal stress. So this concept again we can face in the chapter of thermal properties of matter. Thermal properties of matter. There we get thermal stress again. So sometimes they are linking in this chapter along with Young's modulus. So that is the reason we can simply write that expression to calculate Young's modulus with the help of this concept. Okay, right. Now we will take one rigid support, and this is another rigid support. So between these two rigid support, we are taken one thermal conducting slab. Thermal conducting slab. So for example, soft iron. So this is of length L. Young's modulus Y. Young's modulus Y. Now this is the temperature at room temperature. Now if temperature increases, what happens? Length of the wire will also increases. That means wire is getting elongated. But because of these two rigid supports, there is no scope for elongation of the wire. That means, so because of the length of the wire is increasing, so this part of the wire is applies stress on this rigid support. This part of the wire, because of the expansion of the wire, elongation of the wire, so this part will exert force on this area. So force exerting on this rigid support because of this one, that is called stress applied on this rigid support and stress applied on this support. So because of friction between these two rigid support, so this because of increase in temperature, there is an increase in length of the wire, so it will apply some stress on the rigid support because of change in temperature, that is called thermal stress. So to find this thermal stress, as usual formula we can take Y is equal to stress by strain, but here we will take in terms of thermal stress by thermal strain. Thermal stress by thermal strain. That applies. So thermal stress is equal to Y into thermal strain. Y into thermal strain. Now to calculate this thermal strain, we are having an expression that is called coefficient of linear expansion, that is represented by alpha. Alpha is equal to delta L by L into delta T. So regarding this coefficient of linear expansion, we may have discussed in the chapter of thermal properties of matter. Now strain is nothing but elongation by the original line. So delta L by L is known as thermal strain. Then we can write delta L by L. In the place of delta L by L, we can write alpha into delta T. That is equal to Y alpha delta T. In the place of thermal strain delta L by L, we can write alpha into delta T. So thermal stress is equal to Y alpha delta T. Y alpha delta T. So thermal force is equal to, so force is nothing but stress is nothing but force by area. So force by area will come this side. That means Y A alpha delta T. So this is thermal force. Thermal force. Now if thermal stress will be remains constant, that means we are taking two wires of different materials. In both the wires there will be same stress applying on the two wires. Then what happens? Thermal stress will be remains constant, which means Y alpha delta T will be remains constant. So thermal stress will be remains constant for same reagent temperature. Then we can write Y alpha is equal to constant. We can write Y1 alpha 1 is equal to Y2 alpha 2. Y2 alpha 2, or Y1 by Y2 is equal to alpha 2 by alpha 1. This is the relation directly they asked in the previous NEET examination. So what is the ratio of Young's model if thermal stress is the same for the same reagent temperature? So for the same reagent temperature, thermal stress will remains constant. Then Y alpha is equal to constant. That means Y is proportional to 1 by alpha. Or Y is inverse proportional to coefficient of linear expansion. So Y1 by Y is equal to alpha 2 by alpha 1. So this is regarding thermal stress. So thermal stress will apply on those two rigid support because of this wire, because of change in temperature. So thermal stress is equal to Y alpha delta T, whereas stress by force is nothing but stress by force by area is nothing but stress. So thermal force will be equal to Y A alpha delta T. For same thermal stress of same reagent temperature, Y1 alpha 1 is equal to Y2 alpha. Thermal stress is equal to constant, so the Y1 alpha 1 is equal to Y2 alpha 2. So after this, based on this Young's modulus alone, so we have a concept of Poissons ratio. Poissons ratio. So we will discuss again Poissons ratio. We can go for numericals related to Young's modulus. See this? The area of cross section of the wire is 10 to the power of minus 5 meters square. Area of cross section is A, which is 10 to the power of minus 5 meters square. When its length is increased by 0.1%. So length is increased by 0.1%. That means elongation is 0.1% of original length. This is equal to 0.1 by 100 into L. That is the elongation. So a tension of 1000 Newton is produced. That means force applied is 1000 Newton. the Young's modulus of the y is, as usual, direct formula of this question, y is equal to FL by A. So without giving this elongation directly, they given length increased how much? 0.1% of its initial value. That means this one. So in the case of elongation, F is 10 cube, L is L we can take right as L. Area of cross section is 10 power of minus 5. Elongation is 0.1 by 100 into L. Now this L will get cancelled. This 100 will come outside. So 10 power of 5, 10 power of 5. Again this is 10 power of 10. 1 by 10. That means 10 power of 11 Newton per meter square. That is the Young's modulus of the wire. Elongation they given in terms of percentage. So iron wire of length 4 meter and diameter 2 mm is loaded with a weight of 8 kg. So length of the wire is 4 meter. Diameter D is equal to 2 mm. That means radius is equal to diameter by 2. This is 1 mm. That means 10 power of minus 3 meter. That is a radius. Is loaded with weight of 8 kg. So weight is nothing but weight is equal to tension. That means when y is like this, when y is varying m, mg is equal to tension applied. So tension is equal to mg. Tension is nothing but force, or weight is nothing but force. Okay, right. Now 8 kg is given, that is mass is given. So they given a term of weight, but they given 8 kg, which means when we are taking the value about mass and weight, we need to take the units. So by considering unit of this mass and weight, we need to decide whether they given mass or weight. So in terminology, sometimes they will give mass and sometimes they will give weight. So we need, in the case of mass and weight, to differentiate whether the given value is mass or weight, we need to go with units of the now 8 kg is given, that means mass is given. So mass is equal to 8 kg. The Young's modulus is y value is also given, 2 into 10 power of 11 Newton per meter. So then increase in length of the wire is, what is the elongation produced? So y is equal to FL by A into E. So in the case of hanging part of the wire, so what is the weight we are giving? That weight is nothing but tension. So in the place of force we need to take tension. So now tension is equal to mg. So TL by A into E, in the place of tension we need to take mg into L by A into E. So mass is given 8 kg, G value is 10, we can take, L value 4 meter, area of cross section, find area of cross section we need to take pi r square. So pi into r value 10 power minus 3 meter, 10 power minus 3 whole square, that is 10 power minus 6. Elongation value we need to find. So elongation is equal to mgl by A into pi. That means mgl by pi r square into pi. Mgl by pi r square into pi. So by substituting values, we can calculate the value of elongation. Okay, that elongation is 0.51 mm. Next, two wires of different materials, each 2 meters. So different materials, which means Young's modulus is different. Young's modulus is different. Each 2 meter long. That means L1 is equal to L2 is equal to 2 meter. Are joined in series. So in series combination, Ys is equal to 2y1, y2 by y1 plus y2. That we already calculated. Now join in series to form a composite wire. What force will produce a total extension of 0.9 mm? So elongation must be 0.9 into 10 power of minus 3. Then, so for this elongation, what is the force we need to apply? So in the combination of the wires, we can take y is equal to FL by A into E. But here in terms of taking this single Young's modulus, we need to take Young's modulus of this series combination. So in series combination, we can represent with Ys is equal to FL by A into Y. So in the case of Ys, we can take 2y1 y2 by y1 plus y2. That effective value is already given. Now y1 y2 values are separately given. So from these two separate values, we can find Ys value. So that from that series combination of Young's modulus, we can calculate. So from that, we need to calculate the value of force. Force we need to calculate from this. Force. Okay. Right. Two pipes of diameter 0.25 centimeter. Diameter is same. One instead of steel, one is made up of steel and another made up of brass. One is the steel wire and another one is brass wire. That means Young's modulus are different. That is the meaning. Loaded as shown in the figure. So figure is given like this. The length of steel wire is 1.5 meter and that of brass is 1 point. So y1 Young's modulus is given. Lengths are also given. So elongation is. So elongation of the wires are given. What they are asking? 2y is given. Now, so what is the value of elongation? The elongation steel wire is into 10 power minus 4. This value we need to find. So dash into 10 power minus 4. That means elongation produced in the steel wire we need to find. You see here. So this is of steel wire is attached with 4 kg mass. This is of brass wire attached with 6 kg mass. You see, what is the reason for elongation of the steel wire is, for example, tension in the steel wire T is nothing but, so T at this point, that means at this rigid point or at this point. So what is the tension of the steel wire is, this steel wire has to hold both 4 kg mass and 6 kg mass. 6 kg mass. Now elongation is equal to FL by A into Y. In the case of F, we need to take tension. So TL by A into Y. This is the expression for elongation. Now, when we are finding elongation of the steel wire, we need to take elongation of steel wire. So steel wire has to hold both 4 kg mass and 6 kg mass. If a brass wire is also having some mass, means 4 kg mass plus brass wire mass plus weight mass. So 3 entire weight what is present in this area, we need to, the steel wire has to hold that weight. Now as brass wire and steel wire negligible mass, we can take attached with 4 kg and 6 kg. That means elongation produced in the steel wire because of these two masses. That means M1 plus M2 into G. M1 4 kg plus 6 kg into G. That is nothing but tension. Tension in the because of this weight and this weight into L by A into Y. That is equation number 1. Okay, right. So what is the tension in brass wire? So brass wire has to hold only this is 6 kg. So this is of mass M1 and this is of mass M2. So brass wire has to hold only this 6 kg. That means while finding elongation in brass wire, we need to take only mass of the 6 kg. That means mass of the second body into G into L by A into Y. That is equation number 2. Now this is 10GL by Y. This is 10TL by Y. So by substituting values, we can get the value of elongation of the wire. That will be 1.5 10 power minus 4 here. Then that means this value will be 1.5. So options A 1.5, 2.5, 0.5 or 2 like that. There will be options. We need to go with 1.5 is the answer. Okay. So in the case of hanging of the wires like this, we need to hold. So simple. So tension is nothing but to holding capacity of the wire. So it has to hold both the masses. brass wire has to hold only one mass, that is enough. Okay, that is the key point we need to consider for this numerical. Right. Yes. The elongation will be, so elongation is equal to original length. Stress is numerically equal to strain, means elongation is equal to original length. So y is equal to stress by strain. That means strain is equal to stress by y. If both are same, that means we will get cancelled, which is equal to 1. So E by L is equal to, strain is nothing but elongation by original length. E by L is equal to 1. Therefore, E is equal to L. Elongation produced in the wire is, final length will be 2L. Elongation is L. Elongation is 100%. That means equal to original length. Elongation is equal to original length. So two wires of same length. So length is the same at material, but it means y is the same. Two wires of same length, material, which means Young's modulus is same. That is the meaning. But with radii is different. R1 are loaded with the same weight, which means force or stress will be remains same. Force will be remains same. Now, what is the elongation? Elongation is equal to Fl by A into y. Force is same. Length is same. Force is same. Length is same. Area of cross section is different. Same material. Y is also same. That means E is proportional to 1 by A. That implies 1 by pi r square. That means E1 by E2 is equal to R2 by R1 whole square. Inverse proportional. Okay. So that means elongation and radius of the wire are inverse proportional. That we can take the wire which is having thin elongation, radius is less, elongation will be more. So E is proportional to 1 by R square. So thin wires extends more. Thin wires extends more. Because elongation and radius are inversely proportional. These are also same. Now you see, when a metal sphere is suspended at the end of a material wire, its extension is 0.4 mm. Extension is 0.4 mm. This is 0.4 into 10 power of minus 3 meter. Another metal sphere of the same material. So another metal sphere of same material, which means Young's modulus will be remains the same. So with its radius half of the previous value, that means R1 is equal to R, R2 is equal to R by 2. R is equal to R by 2. So then previous value. So suspended, then extension will be. So they are asking extension value in the second case. That means Fl by A into y. Now Young's modulus is remains the same. So they are not given about this one, but it is suspended. That means in the case of suspension, T will be F will be replaced by T. So TL by A into y. Now in the place of T, we can take mg into L by A into y. Now here, in the place of m, we can take volume into density into gravity into L by A into y. Now what is volume? Area into length. That means volume we can write as 4/3 pi r cube into volume is 4/3 pi r cube into rho into g L by, this value is pi r square, area of cross section pi r square into. Now here area of cross section we are taking same wire, we can take this is A. That means elongation is proportional to R cube. So now, so here density, they given density Density also remains the same because this is made up of same material. So density is same and Young's modulus is also same because made up of same material. Elongation is proportional to R cube. So from there we can calculate the value of elongation. So this is as usual we have calculated natural length L1 T2 minus L2 T1 by T2 minus T1. When the tension on Y is 4 Newton, when length is L1, when tension on Y is 5 Newton and length is L2. Find its natural length. Direct formula of this question. So this is the model of question they given in NEET examination. The following 4 wires are made up of same material, which means Young's modulus is same. Which of these will have the largest elongation with the same tension? So tension is same. What is the elongation? Now we have elongation is equal to FL by A into Y, that is TL by A into Y. A into Y. Now tension is the same. Made up of same material, elongation is also, Young's modulus is also same. Now we can take this is equal to L by pi R square. That means elongation is proportional to L by R square. So diameter is given, half of the diameter is nothing but radius. So for each option we need to find the value of L by R square. L is 50 centimeter, R value is 0.25, diameter 0.5, so radius is 0.25 mm whole square. So for every option we need to find the value of L by R square. For which of the option E by L by R square value is more, so for that value elongation is more. So large elongation means we can L by R square ratio for which option is more, so that wire is more elongated. So more elongation means Young's modulus is less. That means that is a less elastic material. So E is proportional to 1 by L by R square. Okay, right. Now you see this, sir? A copper wire and aluminum wire. You see, when copper is given, aluminum is given, Young's modulus are different. That is the reason they given copper and aluminum Young's modulus differently. Lengths in the ratio 3:2. That means L1 by L2 is equal to 3/2. Diameters D1 by D2 is equal to 2/3. And forces applied in the ratio 4:5. F1 by F2 is equal to 4/5. The ratio of increase in length of the two wires. Elongation. So elongation E1 by E2 is equal to elongation, you know, FL by A into Y. Diameter is given. In the place of A we can write pi R square into Y. So Y is also different. So E1 by E2 is equal to F is different, F1 by F2 into L is different. Lengths are also given in the ratio. That means L1 by L2 into radius inverse proportional. So R2 by R1 whole square, because radius is inverse proportional, and also Young's modulus is also inverse proportional. That means Y2 by Y1. So E1 is copper, E2 is aluminum. So by taking this formula we can calculate the value of Young's modulus elongation produced in the ratio of the elongation. So ratio we need to find. Okay. This is also same. Now two wires of same material. So Y is the same. Have masses ratio. Masses are given. So M1 by M2 is equal to 3/4. The ratio of the extension under the same load. Load is the same. Tension is the same. If the lengths are in the ratio, so lengths are given. L1 by L2 is equal to 9/10. 9/10. So then ratio of the extension. So E1 by E2 is equal to E1 by E2 is equal. So then these two wires are made up of different same material. So Y is same, masses are given. So to express this mass into an equation, in general Young's modulus is equal to FL by A into E. A into E. Now this will be equal to tension TL by A into E. As tension is given, we can take in the place of F, we can take tension. But here, as the given masses ratio, this expression we need to write in terms of mass. In terms of mass. So same material, which means density is also same. Density is also same. So this equation must have density and mass. So that's the reason we can take this is FL by AE into multiply with L and divide it with L. This will be equal to FL square by A into L is volume into E. So now in the place of volume we can substitute FL square by, in the place of volume, density is equal to mass by volume. Then volume is equal to mass by density. Mass by density. So here we can take density into E. Now this density will go upside. Now we can write Y is proportional to, or E is proportional to, E is equal to FL square by M, this is D, into Y. Now elongation is proportional to L square by M. Elongation is proportional to L square by M. Why we are multiplying with L and L? That means Young's modulus value we need to express in terms of density, in terms of Young's modulus, and in terms of lengths. Because they given lengths ratio, they have masses ratio, the ratio of this extension, if their lengths are in the ratio, lengths are given. So length is also must be in expression. That is the reason FL square by A, because another expression is also there in terms of volume. So Y is equal to FL by AE, multiply with A and divide it with A. Now this will be FV by A square into, this equation also we can take. In the place of volume we can write mass by density in the place of volume. So why we have not taken this one? Because given data is given in terms of length. So that is the reason in terms of this Young's modulus, length must be there. So that is the reason without taking this expression we have taken this expression to use that length. Otherwise there is no information about area of cross. What happened to the area of cross section we don't know. So that is the reason we have taken FL square by V into E. So from that we can calculate E is proportional to L square by M. So from that ratio we can calculate elongations ratio from that equation. E is proportional to L square by M. Okay, this is due to its own weight. So weight we have to take at middle of the wire. So now we are taking wire which is hanging from the rigid support. So weight is concentrated at center. The reason in the place of L we need to take L by 2. This is center of gravity of the wire. The reason we can take 2 in the denominator. In terms of normal expression we can take L rho Z in the place of breaking stress we discussed. So in this case, in the case of elongation due to its own weight, so weight is concentrated at the center. We can use this expression to calculate elongation. Okay, this 2y1 y2 by y1 plus y2. This is same. Now see, the Young's modulus of steel wire is twice that of the brass. Two wires of the same length of the same area of cross section. So based on that, we can calculate how we discussed earlier. The same formula we need to use to calculate these numericals. Okay. So two wires of same length, same material, that means Y is the same, and density is also same. But radial ratio is given, stressed by the same forces, stressed by forces F and F, respectively to produce equal elongation. Elongation is same. Then ratio of F to F. We need to take E is equal to FL by A into Y. F is equal to Y A E by L. By L. Now F1 by F2 is equal to same length will be cancelled, same material Y will be cancelled, radii is different, that means A, that means R1 square by R2 square into produce equal elongation. Elongation is also same. Elongation is also getting cancelled. So F1 by F2 is equal to R1 square by R2 square. Okay. So R1 square by R2, that means R1 is R, R2 is 2R. So R square by 2R square. That means 1 by 4. 1 by 4. So which of the following has maximum Young's modulus? So steel, copper, brass, aluminum. So steel is more elastic than copper. Steel is more elastic than rubber. So here aluminum is having more elastic. This is same formula in the case of natural length we already discussed. Okay. So these are different, right? This model is also we discussed. Steel wire under brass wires, 4 kg under 8 kg. Lengths are given, length ratio, length diameter given. Find same tension applied. What is which of these will have largest extension? So elongation is proportional to L square by M. Not this, elongation is proportional to L by R square. L by R square. So same model we already discussed. This is NEET 2013 question. So steel, copper wire, as usual, how we discuss, in that way we need to practice. Identify the false statement. Young's modulus of rubber is greater than that of the steel. So steel is more elastic than rubber. This is the false statement. This is also same model. Which of the following substance has the highest elasticity? Steel. This already we discussed. Young's modulus of the wire depends on material of the wire, not on dimensions of the material. The stress required to double the length of the wire. Young's modulus Y is. So stress is required to double the length of. So elongation will becomes double the. So stress required to double the length of the wire. So elongation is equal to original length. That means final length will be equal to initial length plus elongation. So L plus L, which is equal to 2L. So this 2L will come only when stress is equal to Young's modulus. Stress is equal to Young's modulus. Okay. Young's modulus of the material of the wire is equal to the stress required to produce unit strain. So this equal to same point. Young's modulus of a perfectly rigid body. So for perfectly rigid body, elongation is 0. That means Y is equal to FL by A into E. That means anything by 0 will gives infinity. That means infinity. So Young's modulus for perfectly rigid body is infinity. So these are the different questions from the concept of Young's modulus. So all the model of numericals which are related to NEET and JEE mains are looking like this. Okay, you practice some of the questions. I will send you a file. So in that file you will get more number of questions for your practice. So after finish the class, I will send that file. You can practice those numericals. Okay. Now, so today allotted topic Poissons ratio is also there. We will finish this Poissons ratio. And then tomorrow we need to discuss bulk modulus, rigidity modulus, and you will see based on the situation. So then elastic potential energy and stress strain graph. So those are the topics related to this mechanical properties of solids. So we will discuss based on the time slot. Okay. Poissons ratio. So this is the value which is used to identify how the metal is laterally strained with respect to longitudinal strain. Now we can take a wire. So actually wire is in the form of cylinder. Now this is the wire which is in the form of cylinder. So this is having length L. Length L. Area cross section A. Now we are applying stress on this wire to elongate the wire. Then what happened? There is an increase in length of the wire. what happened? Length of the wire is increased to L dash. L dash. That means this we can call it as elongation. Elongation. So when length is increased, what happened to the diameter? So initial diameter is this much. This much. But final diameter is only this much. That means this is A, this is A dash. So length is increased, area of cross section decreased. That means diameter will decrease. So what is the, how the diameter decreases with respect to original? That is called lateral strain. So lateral strain is equal to minus delta d by d. So change in diameter by original diameter. There is some negative sign indicating diameter decreases. Okay. Next, longitudinal strain. Longitudinal strain will be equal to delta L by L. So here length is increased. Now the sigma we can define as Poissons ratio we can define as sigma is equal to lateral strain. Lateral strain by longitudinal strain. Lateral strain by longitudinal strain. That implies sigma is equal to minus delta d by d by delta L by L. So this is the expression for Poissons ratio. So also we can write minus delta d by d into L by delta L. L by delta L. So here theoretical value lies between minus 1 to 0.5 for most of the solids, or practical value 0.2 to 0.4 for an incompressible solid, the value is 0.5 and delta L is equal to 0. That means sigma is equal to 0 when delta D is equal to 0. If there is an increase in length of a body but there is no decrease in diameter of the wire, so diameter of the body, then this is called cork. So for cork there is increase in length of the cork but there is no decrease in diameter. So for that Poissons ratio will be equal to 0. So for a cork Poissons ratio will be equal to 0. Direct expressions and values, so theoretical and practical values on most of the solids have this value minus 1 to 0.5 and for most of the solid 0.2 to 0.4, for an incompressible solid 0.5 and sigma is equal to 0 for cork which is having no change in diameter even there is increase in length of the wire. Right, here one relation is there regarding this longitudinal strain and volume strain. So volume of the wire we can take it as area into length. So area of cross section is nothing but pi r square into length. Now we can apply logarithm on both the sides and logarithm we can write as delta v by v is equal to 2 into delta r by r plus delta L by L. Delta L by L. That implies delta v by v is equal to 2 into, in the place of delta r by r, what is the sigma? Sigma is equal to minus delta d by d. Delta d by d by delta L by L. Now in the place of delta d by d, d means r by 2. This is r by 2. R by 2 will cancel. Then we can write it as ratio delta r by r. in the place of delta R by R, this is minus, we can write sigma into delta L by L. This is equal to minus sigma delta L by L plus delta L by L. Delta by L. That is place delta V by V is equal to delta L is common, delta L by L is common R. We can write this is 1, this is minus 2 sigma. That means 1 minus 2 sigma into delta L by L. So this is the relation between what is this? Volume strain. Volume strain. What is this? Poissons ratio. What is this? Longitudinal strain. Longitudinal strain. So this is the relation among volume strain, Poissons ratio and longitudinal strain. So in the previous examination they given question based on direct relation. Poissons ratio they given, volume strain also they given. They asked about longitudinal strain. So by substituting simply values, you can calculate the value of longitudinal strain. Okay. So this is about the Poissons ratio. So here these are the points what we discussed. These points directly they will ask in the examination. But while relating Young's modulus, bulk modulus and rigidity modulus, this Poissons ratio will come and insert in those expressions. So there we need to use these values of this sigma. Other than that, they will ask the question directly based on this theoretical points and also based on this relation. Okay, you may note this relation. For this is relation among volume strain, Poissons ratio and longitudinal strain. So with this we completed Young's modulus related topics. Okay. So now from the chapter of mechanical properties of solids, interatomic forces and intermolecular forces, interatomic and intermolecular forces. Next one, stress and its types, strain and its types. Next, Young's modulus. Before this we completed Hooke's law, Young's modulus, and then Poissons ratio. Poissons ratio. So these are the topics we completed so far. Next, bulk modulus, rigidity modulus, and elastic potential energy, stress strain graph, and then relation among Young's modulus, bulk modulus, rigidity modulus, including with Poissons ratio. So those are the concepts remains from this chapter. So tomorrow we will try to finish bulk modulus, rigidity modulus and elastic potential energy. Okay. Thank you. I will send the file. You practice the numericals from that file. Okay. Thank you.